Regarding conferences, it is fun to attend, meet other people, have conversation with others in other companies. You get opportunity to see how other companies use C++ from the build system all the way to packaging and distribution. It's very interesting, and everything in between. In CPPCon, and other conferences, I just mostly been in CPPCon. You get to see a lot of people from the committee, and so you get a first-hand impression on where the standard goes. So it's very interesting if your employer can chip in and send you. It's the problem is it's 5 days, so it's very long. So sometimes it's really hard, but it worth at least being in one of them. And today there's a lot of conferences out there, so just pick one. And not all of them are 5 days. So welcome to the 66 meeting, September 17. I prepared a session on CMake, and if you're new to this meetup, we meet every month, usually Tuesday. It's about an hour. Hopefully that's what we have today, no more. And we just discuss anything related to C++. The whole idea is to learn something new. So the goal is by the end of the hour, you have something useful that you learned, and you can use. And sometimes we have kind of forward-looking features. I'll bring other speakers. We had Bryce few months ago, and he had a very nice talk about the future of C++, 26 and 29. If you have anything that you would like to discuss and you want to present, by all means, just let me know. I'll accommodate that. I'm just waiting for people to come and present. That's a good thing, and you learn a lot of things when you present. Today, as I mentioned, we are going to talk about CMake, more than CMake, to be exact, for C++. This is coming from a book that I'll show in one of the slides. It's a relatively new book, second edition, more than CMake for C++, building cutting-edge C++ code, deliver high-quality solutions. It's a very good book that I recommend. I'll show the book in a second. Just a couple things about myself. I work in NVIDIA. You can find 2 CPP cast sessions with me. I also had opportunity to work with Dorothy on an object-oriented, kind of a modern object-oriented book with C++. Yeah, that's a very good resource if you're looking to read about object-oriented. She did a very good job, Dorothy, on that. So let's talk about CMake. This is not the first time I'm either myself or others speak about CMake. We actually had Eric Hall, he's from NVIDIA as well, talking about Bazel, which being used in NVIDIA quite a lot. My team in NVIDIA using CMake, but there are other teams using other build systems like Bazel. I had at least one in the beginning of our sessions establishment, maybe in the first year, but we also had Alex ranking session 52, a very good session about CMake and best practices that I actually went back when I prepared the slides, went back to kind of refresh my memory with all the good advices that Alex had. He has it's a very technical one. I'm gonna stay a bit more high level just to discuss the opportunities that you have when you work with CMake. And I hope that we would have about 5 minutes maybe more at the end before 6 p.m. To discuss all kinds of things about CMake, because I know that build systems, just like anything else in the industry, there's a lot of pros and cons, and people would like to share their experience working with CMake. The reason I really pushing for specifically CMake, but not only build system, is that I think that in addition for us being a C++ developers, the idea of understanding very well how the build system is taking, how the build system takes the code and creates the artifacts is super important. In other words, I don't believe in the fact of leaving the build system to some other group. Well, obviously there might be a group in big companies that work on CI and CD and all of that, but the ability to understand how the build system works, to go and make good, not hackish, not hacky changes in your build system files is very powerful. And I know in fact that if you familiar enough with the build system, in this case CMake, because I'm using CMake a lot, but I used to be working with a lot of other different build system. We'll talk about, like, I have a slide about some of them. It doesn't really matter. The fact is I'm using CMake right now, and I know that being able to read and make good changes, when I say good, is they are working correctly, I understand the language, is definitely less frustration that can happen when you're building your software. So this is the book. This is the second edition. And first of all, thanks to Packet for providing this opportunity for me to review the book, and I found it very useful to present it here. So if you have a chance to either take purchase the ebook or the printed one, I highly recommend. I know enough about CMake because I'm interested in that domain. I learned a lot of new things in just by reading the book, and I read about 70% of the book, so I have about a couple more chapters, 2-3 more chapters to kind of complete. And since I'm familiar with CMake, it was fast for me to go over the book and just learn the things that I wasn't aware of, and the book did definitely provided all kinds of good things about on the language that I didn't know. So recommendation from my end is definitely high. So why CMake? Not why CMake is like why I present CMake. I just find it popular enough to present, but other people they definitely like other languages. So Alex had similar idea, like similar slides where he shows the popularity of CMake. So CMake definitely is very popular. There are few like annual surveys that JetBrains and C++ ecosystem, all kind of surveys that you can find online. So this is just from 2023. I couldn't find a more recent one, but definitely CMake is at the top. Like, people use it a lot. Just a small disclaimer. This is not my first talk about CMake. I had at least maybe 5 of them, some of them in my previous company, and it's really hard to get everything in 1 hour, or not even 1 hour, more than 1 hour. I had a session with 2 or 3 hours, and it was still hard to fit everything that you can see. It's a complete talk. There is no such thing. so many things in this language, in this build system language, that the goal, at least today, is for you to make notes. So when you do need to, yeah, I'll be sharing the slides like every time. Yeah. So when you need to do something, oh, I need to create a target, or I need to work on install, you at least know, okay, this is the thing that the language provides. Let me go and read about that. And this book is a very, it's a very good resource to go and get a complete understanding of how to do it in the best practices way. So that's the important part. I'll talk about modern CMake. So CMake, kind of 20 years, somehow like 20 years. Started with, I actually started with 2.x. It was horrible, by the way. CMake before 3.x was a horrible language to work with. And I worked on big projects with 2.x. It was all hacking the build system. We couldn't actually figure out what's going on. Unfortunately, lots of people actually carrying these practices to the modern version of the language or the build system. But the CMake provides new commands, expressions that are much better. You actually should use them and not the old ones that are kept for backward compatibility, but you should not use the old ones. If you do use the old ones, you actually falling back to the mess that we had in 2.x, and it was a huge mess in 2.x. So 3.0 and then 3.11, 3.30, which is kind of the latest one. I think there is also 4.x now in the works, or maybe already out. But I'm working on 3.28, which is really good in terms of it's very recent. If you hack it, it's going to be very hard to understand what's happening. It's going to be very hard to find bugs. You'll get a lot of surprises, and it's very, very frustrating. So keep working on, if you do work with CMake, keep working on the modern side of it so everyone can make sense of it. So Kitware, a National Institute of Health, created that. So CMake basically, it's someone said something I saw in the screen, but yeah, I'll do that. There's at least one slide that talks about targets, and so I'll try to remember to highlight that. But there are very important parts that are new. So hopefully, if not, just ask me at the end. So CMake, basically, the whole idea is that it generates files that a specific build system would be using. So if you're using Ninja, if you want to use Ninja as your build system, you tell CMake, hey, I'm going to write CMake code, but please generate code that Ninja, which is a build system, can use. So it's basically kind of like you write code. It's going to translate it to your final build system. It can be Ninja, Apple, Xcode, Visual Studio, or just GNU Make. And from that point, it's going to build. Once you generate, then you can build using the underlying build system. That's the whole idea. I do want to highlight another project that looks fun. I actually used it and I really enjoyed using it, which named CMake. So CMake. So this is a project that you can. It's actually different. It has a different language. It's not CMake. But the interesting part that I noticed with CMake is that it can generate intermediate files of CMake and also Meson, but CMake is what we are talking about today. So the nice part of make is that it would generate files that are good practices. So if you want to know, if you know CMake and you want to know like how CMake is generating, or what is the best practice for CMake, writing CMake, CMake is doing a very good job generating CMake files that are easy to understand, and they are good practice. So I actually learned a few tricks, but just by looking at the intermediate files that CMake is emitting. So before we go into CMake, I just want to talk about like what we had in the past, and then we'll jump to CMake. So there was like build evolution, I call it. Like we used to have, especially when you learn about programming like C and C++, you usually deal with one single file, and you compile with a single file, and then you have multiple files, and you start dealing with dependencies and libraries. It's really hard to start writing scripts that would do that for you. It becomes very cumbersome, and you'll end up writing a small build system if you do it yourself. GNU make files are at least used to be great, but complexity of our builds went up. I think GNU make files and then automake autoconf, which I never really liked, especially because they were cluttering the build the build tree. It was all in build, all the autoconf automake files, which are not checked into your repository, whatever it was SVN and CVS and now Git. It used to be very, very cluttered. Maybe there is a different way to have it like out of tree build, but every single project that I was on, and I've been in a lot of projects that use automake and autoconf, it was all in tree build, which cluttered the build. I already mentioned Bazel, which a lot of groups are using Bazel. They like Bazel because, and it was SCons, but I use SCons just a bit. The people that like Bazel and they don't like CMake, mentioning that Bazel has a better scalability in terms of parallel. It's easier to write parallel builds versus CMake. So just bear that in mind. It's another opportunity that might be as popular as CMake one day. It's not the case today, but maybe one day. So when CMake was formed, there are a few goals that they wanted to keep. One of, for example, they wanted to have it truly like cross-platform. They had all these bullets that you see on the screen as things that they wanted to be as features. They wanted these features to be part of CMake. They wanted it to be cross-platform, Linux, Cygwin, Windows, everything. They wanted a good integration with IDEs, and we do have some slides about the IDEs and IDEs integration. So it should generate something that IDEs can consume. That's the whole idea. They wanted to have it in the right level of abstraction, so you can write something, express it enough, and not deal with how it's being generated into the actual build system, which sometimes it's a mess to read that, like what is actually generated. Like if you read what CMake is generating, Unix makefile or even Ninja, it's really hard to read. Like it's easier to read the CMake. It's much shorter. And yeah, they wanted all the way to testing. So that's something that that was one of the goals. The process is pretty simple. You write your CMake list.txt, multiple of them. And one thing before I forget, the book has one chapter about how, because I know a lot of people, especially newcomers, I see it in Reddit, they have issues to create a proper C++ tree. They have issues dealing with the absence of package manager, we talk about the small package manager that CMake comes with. Obviously, it's not a full-fledged one, but it's something that very common and used a lot in the industry, probably number one, because it's there as part of CMake. We'll talk about it. And so a lot of people, they don't know how to create a correct tree with include files and source files, separating it maybe to libraries, binaries, like executables, testing, packaging, all of that. The book has a chapter on that one, which is really good. So make a note to take a look at that. So when you after you write your CMake or CMake list.txt, you can have one or more because your build might be very complex, and lots of subdirectories. Then you generate the files. There is another step, which is a configuration step. I'll talk about it later. But I'm mostly going to talk about configuration and generating the build files as one step, though it's two different steps. You usually, when you say, I'm going to generate the files or regenerate the files because I made changes to the CMake, configuration is something that happens automatically for you, and I'll talk about it. And then you invoke the build. We'll talk about how to invoke the build correctly. Okay, so some would say that the syntax here is a bit confusing, but here it is. There are two commands here. One is generating, and there are multiple ways to write this command. I'm just showing one of the best practices one. So you can have you can specify where the build tree, like all the artifacts, all the generated CMake files, all the generated specific build system files, where this whole thing goes, like which directory. So you can say CMake dash capital B. This is the directory, and it doesnn't really matter where the directory is. It can be alongside your tree. It can be a build directory inside the tree. We'll talk about. Oh, we're going to talk about it now. So it can be anything. You just specify with a dash capital B, and then it can be implicit. But if you want to say, hey, the build, all the artifacts, everything would go to this directory. The source tree, by the way, is this directory. So you can invoke it basically from anywhere in your file system by saying, okay, dash capital B is here, dash capital S is over there. So there are some ways to have it implicit. For example, most of the textbooks or maybe blog posts online, you create a build directory, like make dir build directory, cd to this build, and then you type CMake space ... So that's like the shortest thing that I'm aware of, where you can say, okay, this is the build system is my current, it's implicitly my current working directory, and the source there is ... like up. So that's like I'm in a hurry. I just want to do something very, very simple. I want to type as little as possible. That's gonna work. CMake is encouraging us to have an out of source build, like completely out of source, like don't have the build directory inside your tree. But a lot of tools or IDEs, they are okay with having the build directory. CMake is not gonna complain. You might need to edit your git ignore to ignore that because it's there is a directory inside your tree, but all the files are going to be inside this build directory. It's not gonna spill outside, so it's kind of contained. So that's one thing. The second command is actually building. So the first one is generating the files or regenerate. Let's say I made a change to the CMake list.txt, one of them. Oh, I want to redo everything from scratch, like from fresh. I'll talk about it. So so that's the first one. The second one is I'm actually going to build. If you notice here, I don't know with the second command, I don't know which build system I'm going to use. It can be Ninja, it can be CMake, I don't know, and I really don't care. So CMake encourages us, and this actually you usually don't see with kind of newcomers to the domain. People would actually invoke Ninja, or they're going to invoke Make, which is less recommended, just simply because you have more options and more knobs to specify when you um, uh, execute CMake command. So you can say CMake dash dash build. This is the build directory, and then you can say, okay, I want to build this target, this specific target. So the CMake is all about being agnostic to your operating system, being agnostic to the underlying build system. So if you tomorrow change your build system from X to Y, if you still, maybe you have a script that is running the build, if you use the CMake commands, it's gonna be correct. So if you move from GNU Make to Ninja, but you were executing Make, when you move to Ninja, this Make it doesn't make sense to run it. But if you were running CMake dash dash build and that's it, it's gonna work with Ninja as well. So that's why I'm gonna repeat myself a lot. You should use the wrapper, the CMake wrappers on top of your specific tool. So being agnostic, like elevating yourself in the abstraction. Usually you start the building. There's going to be a link. You can run test, and then you can also package. It's all within CMake, which is really, really nice. Unfortunately, I'm not talking about packaging and install. It's just too much for 1 hour, so it's not going to happen. But just make a note that this is something that you should look at. So this is probably going to be your first CMake list.txt. You need to specify what is, like, your code is going to be, you would need at least features from whatever version that you specify. By the way, you need to get used to the CMake, just like anything else. The CMake syntax, once you understand, it's really easy to understand, because this version that you see here is basically, it's like a named argument. You'll see it a lot in CMake functions commands. You say, okay, X and then the value. It's like version and then 3.3 and target and the target name. So it's basically like a named argument or name parameter that you would use. So this is the one. So CMake is highly kind of, they did everything they can to be backward compatible. So there are all kinds of policies that would be on when you say, I want CMake of this version. So all kinds of policies and all kinds of features would be enabled for this specific version, and you can use it. Okay, so that is super important. You have a project. This is kind of the smallest project expression that you can have. Hello, it's just the name of the project. But the project command or the project expression has a lot of parameters. You can say, okay, I want this language to be, and the default is C and C and C++. But you can say, okay, I want, since I'm familiar with that, I want CUDA compiler. So this is not a nice to have. When you say I want a specific language, CMake is going to do a lot of parsing behind, kind of under the hood, kind of behind the scene, to get all the stage ready for you. Like, it's going to understand what kind of compilers you have on your system that is available, like in the path and all. Like it's going to do a lot of checks and a lot of preps in order to give you all the variables and facilities to start using the language. So this is important. Since C is kind of default, I didn't mention it here, but you can see that it's actually saying, okay, I'm checking this C compiler and C++ compiler, and there's a lot of other stuff that can happen. And then what I'm doing here is just I'm creating an executable named hello, and I have a CPP file that that I wrote that is going to be compiled and linked and ready for execution. There are no tests here, but that's just the minimum that that I can have. By the way, just stop me if we have any quick question. So again, if you look at the CMake documentation and CMake documentation, they are organized by specific versions. So you have a drop down list. You can say, okay, I want to see the documentation of, because things change, of this specific version. You'll see that I can specify languages. So remember, languages is going to be a name parameter. So languages, and then the languages that I can have. If I have none, here it's by default is C and CXX. There are, if I specify none, like actually writing none, it means that this CMake list.txt is an agnostic script. We'll talk about it in a second, that I want to use. So bear with me regarding that. Just to emphasize something about generating the files. My opinion is stick to this. Not only my opinion, it's just the best practice. It's just I'm kind of enforcing that. Stick to the first one. It's much more explicit, and it's very clear what is your build directive, what is your source directive. Nothing is implicit, because otherwise there are few implicit similar syntax that, yeah, it's gonna work, but it might confuse. Actually, I like explicit more than implicit in this case. Like being like actually saying what you actually mean. So we're talking about generators. So I usually work with Ninja, but Make was also something that was used a lot in previous projects. You should probably pass the -G and the generator name to choose the generator. It's much more explicit, and people that read your code or read your command line, if you just put it in documentation and all, they know that you're actually working with Ninja. Not that it should matter a lot, because again, it's all agnostic, but sometimes you want to pass specific command line options. So CMake allows you to do the following. It allows you to write CMake -- build. What is the build? -- maybe target. What is the target that you want to build? And then you can have -- and all kinds of parameters that are going to be passed to the actual generator. Let's say Ninja. For example, I usually have -v, like lowercase v. So I would have -- space and -v to just get all the compile lines, instead of having that in a quiet mode where you don't see the compile and link lines. You're just going to see a very fast print of the files that are being compiled and linked. But if you want to take a look at the actual what is actually happening with compilation, which I recommend people to at least understand what's happening and acknowledge that what you see is what you really want to build in terms of compile definition, compiler options, linking options, all of that. It's really, really important. So yeah, you can specify the generator, but you have the option to have a specific parameters passed to the generator. Some options are kind of similar to Make and Ninja, but not all of them. Cache file. So cache file is everything that remember I told you that there is a configuration and generation. This is where the configuration happens. Configuration happens only once. So if you pass all kinds of parameter during the configuration, and what does it mean you pass parameter? You pass -d to define something, to define a variable. It's going to be placed in the config stage. And once CMake cache.txt is written, it's not going to be rewritten again unless you, this is something that I learned from the book, because I used when I wanted to start from scratch, I would do few things. Either if I'm lazy, I'm just gonna delete the CMake cache.txt. So I want to start everything from scratch, because sometimes I want to assign new variable to a new value to a variable that was already configured, and it's not gonna reconfigure it again. So this is something that is very confusing newcomers to the language. They don't understand, like, I'm trying to reassign a variable to this specific variable, and it's not happening. It's not happening because the CMake cache.txt has this variable. It's cached, and it's not going to be rewritten since the CMake cache is already there. The build type, if it's debug or release, is one example. The build type, once you set the build type, it's not going to change. You need to remove the CMake cache.txt, or remove the entire build directory, or what I learned is that there is a --fresh option that it's going to remove the CMake cache.txt for you and other files that are important to give you a fresh environment. So if something looks weird, by the way, just use the fresh option, delete the whole build directory. It's also an option. What I want you to do is understand cache variables. I don't have time to kind of go over the differences and all, but just understand the cache variables that are being cached into the CMake cache.txt. I can tell you for sure, this is one of the top issues that people don't understand about how CMake works. The fact that there is only single configuration. Once configuration happens and CMake cache is written, it's not going to be rewritten unless you delete the file. Super important. I'm saving you a lot of frustrations. Okay, another thing that would help you a lot, which is a great help, is all these options giving you the system information, log level that you can say, I just want you to give me warnings. So the build generation, when you build the generator files, let's say the Ninja files, you can suppress a lot of noise and just give you a specific log level of messages. So that's a very nice it's a very nice feature. I'm not going to talk about log contexts, but read about log context to give you a specific information when you generate the build. Trace is a huge helper if you want to understand, and I used it a lot when I didn't understand like what is going wrong with the build, why it's not doing what I wanted it to do. The trace helps me to understand like how things are being evaluated in CMake. So it's going to tell you I'm parsing this file, and if you just run trace, just next time if you're working with CMake, just run trace. You'll see everything that happens in CMake. It's actually reading so many files and parsing a lot of files that you'll be it's very amazing to see that. Verbose, when you run the build itself, verbose or -v. For make files, there is CMake verbose make file. that you can define, Ninja just -v would do the trick for you. So we already talked about --fresh, which is super important. And I'm using it when I don't care. I just want to start from scratch. I always use --fresh since I realized that this is a good, a very useful one. Clean first. When you build and you want to invoke the clean target, so CMake would create a clean target for you. Clean first is really nice. As you say, okay, CMake --build. Here's my build directory, --target, whatever. If you don't specify target, all would be the default, like everything that is registered under all. And then you can say --clean first. It's gonna first run clean, removing artifacts and start all over. But it's not removing your cache file. This is the build, not the generation clean. So if you're aware of these stages in CMake, it helps a lot to understand what's happening. So here's an example of how you use it in agnostic way. You say, okay, CMake --build, the build directory --target. I want to have this executable, this library. Now, if my executable depends on this library, I don't really need, but this, let's say it's just two separate ones that I want to build, and they don't have any relationship. So the exe is not it's not depend on lib. So so this is one way. But if it depends on lib, CMake would do the right thing for you. If you write your CMake list.txt correctly, we'll talk about it in a second. This is clean first. Or you can have target. There is a target clean, so you can invoke target clean. There's also installing project. This is something which usually overlooked, unfortunately. You should look at the install chapter of the book or other books that talk about it. There is a very good chapter on that. The one thing that I discovered as a new comer to the language many years ago is that CMake is actually baking in RPath, because the philosophy of CMake is when I'm running my artifacts, and RPath is embedded, I'm gonna run against things that I compiled against, right? I want to run the executable with my libraries, not the one in LD library path or something like that. So when you run install, it's not just copying files to some install prefix directory. It's actually relinking the whole artifacts, stripping out the RPath. So this is a major thing to understand, a major change between artifacts that are not installed versus installed. It's not just copying files in your file system. It's actually, there is an extra step to relink everything without RPath. So that's important. Okay, so I'm going to talk about running command line tool very quickly. So CMake, as being kind of philosophy, is being agnostic to the operating system and all, can operate as just a shell script, like a shell script. Like you can write scripts in CMake that not going to affect the cache. You just say, okay, -p, this is my CMake script, this is the argument to the script, and just run it in agnostic way. You can basically do all kinds of manipulation to the file system, being completely agnostic. So it doesn't matter if it's a Windows or anything, you're writing script. And what happened is that there are all kinds of utilities. Remember I talked about packaging, the small packaging module that CMake has. It's fetch content, they name it fetch content. So fetch content need to do all kinds of housekeeping. It needs to copy that one, and so what they do is they create a shell-like script. It's a CMake script, and they run it with this option just to have some housekeeping. They want to clone Git, they want to copy things, they want to do maybe patch file. but they want to do it in a agnostic way. So CMake gives you this shim layer, kind of wrapper facade when you write CMake language that is going to be interpreted as a shell commands or whatever the operating system provides you. So this is a very useful thing to understand, especially when you need to debug something that goes wrong and you see that -p with a CMake. Now you understand that they just running some script just to do housekeeping. So that's important to understand. I'm not going to talk about CTest and CPAC. Unfortunately, they are very important, but I don't have time for that. So same idea, creating packages from archives to Debian packages and others, RPMs in a agnostic way, running your test in an agnostic way. So this is super important. Just make sure that you have that in your to-do list when you go and examine that. I don't have enough time, as I knew that it's gonna be a bit more, hopefully not a lot, but it's just 10 before 6, and I see that I still have slides. There are all kinds of tools that CMake comes with. CTest is basically a utility to run the test. So you write code in the CMake list.txt that eventually the CTest is using to run tests, CTest, Cach, no matter, whatever. There are CMake GUI, there are CMake console-based UI to configure and use CMake. I barely used the GUI and CMake. I used it only to demonstrate, oh, this is something that is possible. I already talked about the CMake list.txt options of the project, and also I'm going to skip that slide so I can go to the other stuff. One thing is observability of what's happening, having the tracing. There's also debug mode of running your CMake generation, which is amazingly useful if you happen to be confused about like what is CMake is generating for you. There's also CMake configure.yaml, which is relatively new. 3.26 is very new, so make sure that you have that in your to-do list. You need to remember that you don't have to write functions or macros. Functions are better here because there are functions and macros in CMake, and it's very similar to function in C or C++ versus macros in C and C++ in terms of the scope and all. CMake itself comes with tons of modules to help you write code that you don't really need to reinvent the wheel. For example, is my system is big endian or not? There is a Git repository named Awesome CMake. There is a Git repository that named CMake modules. CMake itself on a Linux-based system provides you over 150 modules, including finding. Everyone is kind of concerned about the fact that C++ doesn't have like a package management, and this is true. This is why we have Conan and VC package. But CMake itself has a way to locate and understand like what kind of packages are installed in the system. And there's also other things which I'll show in a couple of slides. Quickly, find modules. I don't have time to go into details, but this is basically your opportunity to use some expression in CMake to find libraries, programs. Let's say I want a specific program to be located in the system. So find program is helping us, and then you can use the program in order to do something with it. Let's say you want to have program tar to create an archive. So you can say, okay, find program tar. You can hint CMake. These are the directories that you can look for it. And then the variable that would be created for you would be the full path of the tar executable that can use later in your logic. Find program, find library, and other find modules, super helpful. The find package is something that would go and look at the installed modules in your file system. For example, I want to have find CRL or curl. Usually, your Linux-based file system, when you install CMake, it's going to provide you CMake helper files that would help you to locate curl libraries if you have it installed, and then you can use it in your logic in your CMake. For example, linking against curl. Same for Boost or zlib or anything. There's so many of them. I find it. I see a lot of newbies in CMake that actually trying to do it manually, and why doing it manually when CMake provides you the facilities. CMake language is kind of weird. One of the things that you need to make sure that you understand is the at least basic understanding of the language. What is a string? What is a list? Believe me, a lot of frustration would be gone if you understand that CMake is keeping a lot of their data structure in a list. And a list can be something that has space delimiter words or semicolon. It's the same thing. But list is something that is being used. Like if you have, imagine you have multiple path variable that has, it is kept in a list, and you can traverse the list. CMake gives you everything you need in order to manipulate list, append, prepend, remove an item, iterate over a list. But the idea is that you need to understand there is a list. It's an important data structure in CMake. The scope of a specific variable, it can be a string, it can be a boolean, which boolean basically it's kind of a string, or a list, has a scope. The scope would be from that CMake list and the subdirectories, or you can say, okay, I want it to be also in the parent scope. The whole scoping thing in CMake is one of the things that are very, very frustrating for people, and you need to understand like what is the scope that this variable would be applied to. There is also a way to limit scope, which I learned by reading the book. I didn't know there is actually a block. You can think about a block as a curly braces in C++, where you say, okay, the variable that I'm defining is going to be only for this specific block, not for the subdirectories that are under this CMake list. You can reach environment variables with env. The idea behind this whole understanding the CMake language is writing clean code. CMake and like any other language can basically turn into a mess if you're not doing it correctly, just like anything else. Python can be the same, right? So it's very important to understand how to write it in. If you stick to the modern part of it, it's going to be kept very tidy. One thing is that I learned that besides if else for each, there's actually a way to zip list. You can actually take couple lists and zip them and get like a tuple, which is very interesting. I didn't know that CMake has that. Okay, let's talk about targets. So targets are basically the main thing that you're actually building. It can be a library, it can be executable, and you can have your own targets that you're going to define, which are not basically an artifact. You can kind of a custom targets. The important part is that you need to link the targets. When I say link, they kind of logically link in order for all the dependency graph to work correctly. You can actually emit a dependency graph when you see this executable would depend on this target. This target it's a library. So if you write it correctly, you're going to have a very tidy CMake code. The thing that you need to understand regarding targets, libraries, or executables is that when you write the target, when you write, okay, I'm going to define a target. Let's say it's a library. This library is going to be built by these sources, C or C++ sources. The important part is defining what is the, let's say, include path that if I'm going to rely on this target, I'm going to inherit this include path. So this is a very important mechanism in CMake that is, unfortunately, it's super important. I think one of the top important mechanisms in CMake, but it's overlooked. People not actually doing it correctly. And now you can specify, okay, this include directory for the target that I'm defining should be used when someone is actually depending, when someone actually need my library and linking with my library, they're going to have this include as part of the -i, the compile option -i. But sometimes you want to say this include directory is only internal for this library. No one inherited when someone wants to depend on my library, this directory should not be visible. So there is language in CMake to define all of that scope of the include directories, link libraries, like libraries that if you link with another libraries and you need a specific directory, like this link directories can also be visible to targets consuming this other target, or maybe it's internal. So all of that has to be written correctly so you're not going into a mess. What I usually see is people not following these rules, and when I need to depend, like when I have an executable that I need to link with your libraries, I just want to link with your libraries, telling CMake, I want to link with your libraries and all the include path, all the libraries that you need and that I need as well as part of my linkage. All of that information is already encoded in the target that I'm actually linking with. I don't need to go and figure out what are the include paths that your library needs. What are the link directories that you need to add because there are other libraries that I need to link with. All of that should be already taken care of in the target that you write as a library that I want to consume. So that's the important part that is usually missed. It's usually missed and not happening well. You can create dependencies between targets by having this add dependencies. When I have an executable and I'm specifying that I'm linking with this specific target, I'm creating dependencies. I depend on this library. But sometimes there are two targets that usually it's like maybe one is a generated file, let's say protobuf, and I have something that I would like to I depended this protobuf, so I could create these dependencies by using these add dependencies. It used rarely, but when you need that, it's something that you can reach out to. Okay, I talked about package management. So this is the small package management that you should have in 3.11. So basically what happened is in 3.x, 3.0, what we had is kind of a git sub module, and we added, and we said, okay, add subdirectory, parse this git, third-party git, and this is how we used to do that. And then later in 3.0 and until 3.11, we had something named external project and underscore add and other commands that were very confusing, very hard to use. It was, ergonomically speaking, it wasn't good. It was very confusing, but it was better than having this add subdirectory. From 3.11, we have fetch content, which made life very, very easy to consume other packages. And a lot of packages out there on GitHub and GitLab, they are fetch content friendly. Not all of them, but a lot of them. And fetch content friendly means that I can include fetch content. So this fetch content is a module, is a CMake module that is provided to you. It's just a bunch of functions in some CMake that was installed in your system when you installed CMake. And so you include that, so all the functions are now available. Fetch content declare is a function that is now available for us because we included fetch content. And now I can say, okay, this project, fetch it from this Git repository or from this tar or from this source directory on your file system. And you can specify the tag and all. And that's it. You start using it. So what I'm saying here is that it's not cargo. Cargo is a bit more, ergonomically speaking, better. But it's kind of an easier, kind of an entry-level package management compared to Conan and VC package. Well, obviously, Conan and VC package are much better. But this is actually a very good one, and it's going to fit the bill for most of your things. The nice thing about it that I can have different versions of B. It can be V1 and V3 that I'm fetching content. It's going to fetch the content if it's not fetched yet in your build directory, build it if it needs to build it, and set all the include path and everything for you under the hood. You don't need to do anything but just to tell CMake, I'm gonna be dependent on this specific package, and this is YAML CPP example. So this is super handy, by the way. A lot of people say I don't know how to bring packages to CMake. Sorry, to C++ project. This is your probably a good way to do that. So you just need to declare it and make it available, and you start using it. Very easy to kind of Google and be done with it. And it supports CVS, SVN, Mercury, Git, anything under the sun. I already talked about targets. The one thing that I want to mention, I don't have a lot of time, is that there is a transitive usage of targets. So let's say I have a library that another library needs. So another library consumes, then an executable that needs this library. So basically, all this chain would, like, let's say include path. Everything would happen for me on my behalf if I wrote it correctly. Let's take a look, just a couple minutes, looking at this specific file. I have a project of C++. I have an executable that has CPP. I have another executable that has another CPP. So two different executables, two different targets. Now I'm telling CMake, I need to link a specific library. The name of the library is calculations. And I want to link it with the terminal app. I have another request from CMake. I want to link calculations and drawing, two different libraries with the GUI app. Okay. And then I have a library that I'm defining. So calculation, which is CPP, and then drawing, which is CPP. Would this work? The answer is no. Why? Because when CMake is parsing these, there is no calculations yet. There is no drawing. It's defined here. So I need to move these libraries on top, and it's going to be recognized. So just make sure that the order matters. So when I refer to a specific target already needs to be defined. I talked about your own custom target. So this is an example of a custom target that is running couple commands. So there is a shell dash C, another shell dash C. Basically, it's running checksum on and of the specific executable, redirecting the output to something that's CK. Again, with the other executable, the byproducts are CK. So basically, I can actually use this byproduct as a dependent uh, element. So that's something that I'm not showing here, but be aware that you can basically build dependencies using all these byproducts, uh, named variables or named arguments. This is just a comment. So add custom target, add custom commands are two things that I'm not talking about. They're just too big, but something that you should make a note to understand how it's working. Okay, we're almost done. I want to talk about quickly about C-line as an example of IDE consuming CMake. Just very simple. C-line and CMake are basically working in a very good harmony. It's like C-line was built primary for CMake. I don't know if it's correct because I'm not part of JetBrains, so I don't know if that's correct. But it's integrated so well that they actually have like you have everything that you need to specify what you want to do, what kind of configurations, how to build it. It's like you don't really need to touch the command line, though I really recommend understanding how the command line works. Few versions ago, they actually added debugger to CMake. You actually can breakpoint in your CMake list.txt. And so I did a breakpoint here in this screenshot just to show you that I can actually inspect everything under the sun that the CMake environment provides me. This is a huge benefit. If you don't want to take a look at traces and all, you can understand what exactly. Yeah, CMake is also integrated in Qt Creator. This is true, and Visual Studio. This is true. Thanks for mentioning that. You can expand this environment variable. You can expand this CMake. You can take a look at every single variable. It's gonna make your life much easier if you stick to this, if you need to. More items that I have here: CMake presets, generator expressions. There's so many things out there. CPAC has 20 models. By the way, CPAC has 20 models are part of the book. So the CMake has support, and there is a chapter in the book for CPAC has 20 models. So this is actually nice. Presets, also generators, are part of the book. I highly recommend looking at it. So that's basically it. That was my last slide. I have a bunch of resources that you can take a look at. Just collected. I thought that would be very useful for you. I'm 11 minutes after 6, but if I'm going to open the floor for just questions about CMake and experience and everything else that you would like to discuss. So yeah, if you have anything, yeah, just go ahead.
Yeah. Hello. So thank you for the talk. It was great. I'm like a newbie, I guess, to C++, and I guess CMake too. And so I've been like trying to, wrap my hand around CMake. And the other day I stumbled upon the presets, which you mentioned in the one of the last slides. So I was wondering if, like, first of all, do you have experience with the presets? And if so, is there a reason to use the just basic CLI over presets? Because I feel like the presets were like super ergonomic.
Yeah, so presets basically I can't remember exactly, but they are recent. They were introduced maybe 18 months, couple years, so it's new. From my experience, a lot of build systems in what I see around not migrated to use presets. It's actually on my to-do list to do it in for my group, for my team, because I think this is, as you say, much more ergonomically, right? If you need something very simple, preset is not gonna, just an overhead to define, but I think it's useful to swap between different configurations. And I believe that Conan working very nicely with presets. So I definitely would like to see presets in my project. And this is going to happen soon. And I think this is something that's worth spending time just understanding the idea behind preset file, how to invoke it, as opposed to, oh, I'm going to have this all dash Ds and all of these options in the command line versus, oh, have this configuration file, the preset configuration file, I'm gonna use it. So this is something that I haven't used much besides just reading, but this is something that I'm definitely would like to migrate my build system to.
Okay, cool. Thank you.
You're welcome. Other questions, comments? Okay, so I'm going to, before we leave, I'm going to just put the most recent Discord link. Feel free to join. If you want to continue discussing CMake, I like discussing CMake. I like build systems, not only C++, but also build systems. So feel free to share ideas, tricks, anything that you can think of in our Discord servers. Thanks for attending. Thanks for joining me. Hope to see you next time. Take care.